Okay, let's take a look. What are the conservation laws? Now, in terms of this class, we so far. So we started from by briefly talking about the motion, right? So one-dimensional motion. So that is chapter number 3, right? Chapter number 3 and chapter number 4. We talk about 1D motion, and then we understand the projectile motion, that is actually 2D motion. And we can use the same concept to understand the 3-dimensional motion if you want. So in that 2 chapters, what we done, we interested only objects motion from one point to another. It doesn't matter which direction is x-axis, y-axis, anyway, it doesn't matter. What we interested is actually how the distance or the position change, what is to about the rate of change of displacement, and we talk about rate of change of velocity, right? By using only those concepts, we can actually understand the object motion. And then if you know certain information, you can predict what's going to happen next, or we can investigate what happened previously, right? So that's the idea on those 2 chapters. And then followed by that, chapter number 5 and 6, we talk about Newton laws, right? When it comes to the Newton laws, we're talking about what are the forces acting on the object, what happen under forces, then again the acceleration appears, and then we can still use this concept on chapter number 5 and 6, and then beyond, and then even physics 2, even physics 3. But depending on the situation, we may interested some other parameters than just the motion of the object, right? So what we interested is in chapter number 5 and 6, mostly about the forces, what kind of forces acting on the object, and then we try to understand the situation by looking in the direction of forces, right? So still object can move, object can stay at rest or move. Still these can apply accordingly, but we more interest the forces. And in chapter 7 and 8, what we actually discuss is about the energy, same kind of questions, but we interested not the forces, not the motion or anything. We just interested about what happening to the object energy. What are the type of energies objects can have, what happening to these energies, and then so on. Now in chapter number 9, what we're trying to do, we're trying to understand the momentum of the object. So basically why the momentum is needed, we try to understand the collision of collision of the object, this chapter 2. So until now, we never talk about collision, right? The chapter number 1, 3, 4, 5, 6, or 7, 8, we never talking about the collision of the object. We always talk about the as object under certain forces, object can move from one point to another, but we never discuss about the collision, right? Now, this chapter mainly we interested about if there's a collision, what happening before the collision and after collision. That's what we really interested. So, which mean basically we can say I have a two object. If there's a collision, we need to have more than one object, right? We can say object number 1, object number 2, and object number 1 can move into x direction. Object number 2 also can move into x direction. Let's say this is before collision. Because of that, I can say this is object number 1 initial, object number 2 velocity initial. That I represent initial means before collision, right? Like similar to the concept of energy problem, you remember there was the initial condition and the final condition, but we never talk about the collision there, right? So in this case, we interested what happened. At some point, these two objects will collide each other, and then after collision, maybe both objects moving into the same direction, maybe one can bounce back. We don't know what's going to happen, but we can study that. So what happened after collision? Object 1 can change its velocity. Object 2 can change its velocity. Object 1 and 2. And then we assume mass is conserved always. Mass is not losing at all. So if there's a collision right here, then we try to investigate what happened during the collision. Whether there's any energy loss, whether there are some other forces acting on the object. That actually planned for this whole chapter. when it comes to collision, there's a different type of collision we can investigate. There's two type of collision in general. So all the type of collision you can convert it, you can divide into two. One is called the elastic type collision. Other one is actually called the inelastic type of collision. Elastic type of collision means energy is conserved. Okay, so which means changing energy should be zero. Energy total final minus energy total initial must be zero. So which means final energy should be equal to the initial energy. Which means during the collision, there should not be any energy loss. Okay, that's the idea. On the other hand, inelastic type collision means energy conservation is not valid. So energy actually can lose. During the collision, energy can lose. Generally, most of the collision are inelastic type of collision because some sort of energy can lose during the collision or convert into other type, right? Like there's a collision, you will hear some sound, which means sound is the energy type of energy. And if there's a collision, maybe there's a fire, the thermal energy can be produced. So that means the mechanical energy can be converted during the collision. Okay? However, if I investigate the momentum of the system before and after the collision, that will tell you a completely different story. Now, if I take a look momentum of the object, how we define the momentum, if there's a moving object, if object has a velocity v and then mass m, that object has a linear momentum. Momentum is always a vector. Linear momentum p is equal mass times the velocity of the object. Momentum is always a vector, okay? Linear momentum. Every moving object has a momentum, right? Like the kinetic energy, every moving object has a momentum. If the object is at rest, there's no momentum. So this is one way of defining the momentum. The later you will see we can define another way the momentum, because momentum is actually m times the v. However, if you can take a look this in terms of concept of Newton laws, we know force is equal mass times the acceleration. Acceleration is rate of change of velocity, right? So which means I can write force is equal mass times rate of change of velocity. If you bring the mass in here, then this is going to be rate of change of product of mv. Product of mv is the momentum. So we can write force is actually d linear momentum over dt. So force is actually rate of change of momentum. So now you can see earlier in chapter number 4, chapter number 5, 6, and 7, 8, we talk about forces, but we never talk about force as a function of rate of change of momentum. But if there's a collision, this is actually very important. If there's a collision, during the collision, if external force is acting on, momentum of the object must be changing. So this is rate of change of momentum. So the rate of change of momentum means during the collision, or if you have a force applied on the object, the momentum is changing. That makes sense because let's say I have object here, I apply a force this direction, will drag the object x distance along the x axis. Then as a result of that, you can see initial velocity, let's say vi. After some time, it has final velocity because it is under acceleration. So the momentum is P initial is m times v initial, P final is m times v final. So which means definitely now momentum is changing. If there's a force acting on the object, external force, okay? This should be external force. If there's an external force acting on the object, momentum must change. However, this is important concept for the collisions. If you go to the collisions, let's say I have two objects, and then before the collision, both objects are moving. V1 initial, V2 initial, and then two objects are collide some point right here. Then after collision, let's say both objects are moving again, but different velocities. V1F and then V2F. Now, during the collision, if you take a look, we'll assume there's no friction, and then there's no any external forces, okay? No any external forces. If you assume that there's no any external forces, and then if you take a look the object collision point right here, during the collision, that common surface, this is the two object, I'm drawing it larger now. And then both object now colliding, so which means object number one pushing the object number two, there is a force acting right here on object two due to object number one. Be carefully observe how we naming this, right? What this telling you, if to one, this two is where's the object is where's the force is acting on. Which object this force is acting on? Object number two. Which object this force is creating, or which object where this force is from? Due to what? Due to which object? So that actually this number represents. This is not 21. This is force to 1. Force acting on object number 2 due to object number 1. Now, if you look at the Newton third law right here, exactly on the surface, if you have a force, there should be a reaction force, action-reaction force. Because of that, during the collision, there should be a force on object number 1 due to object number 2. Now, if I consider the net force right here, exact this moment, net force, you can see force F1 and force F12 and F21, magnitude-wise equal, and then direction-wise opposite. These two forces are magnitude-wise equal, direction-wise opposite, so which means if net during the collision is actually 0 if there's no any external force. All the internal forces during the collision will cancel out. So which means if I go back and take a look what we developed earlier in terms of Newton's second law, in terms of momentum point of view, you can see if the force is 0, then the changing momentum must be 0. Now we can say the force should be delta P over delta T. If the force net is 0, then I can simply say the time can't be 0 at all. This part will never be 0 the time, because of that delta momentum is actually 0. So the momentum must be conserved no matter what type of collision is. What important is that there's two types of collision. We divide the collision into two types by looking at the energy. However, if you look at the momentum during the collision, only one thing we have to take a look whether there's external forces or not. If there's no external forces, doesn't matter what type of collision is, then the momentum going to be always conserved. So that called the momentum. It's going to be 0 any external forces. Okay, external forces, those are very important technical terms. Okay, if you don't care that part, external part, then we can't define that because there's internal forces always, right? Internal forces there, but internal forces cancels out during the collision. This will be common for both types of collision. Okay. Oh, okay, question. All right, then let's continue. That's what we try to understand in this lab, right? So the main plan is to create the collision between objects given some velocity, knowing the masses, and then we're going to investigate by measuring the velocity. We can investigate all those information, right? All I need is actually two objects and then let it collide, right? So that's all we need. I need to have a two object. Object number one, object number two, then we'll apply a certain velocity for object number one and object number two, V1, two initial. One initial larger, then these two will collide some point here. After collision, both of them will go into the same direction, or one can bounce back. There's different thing happen, doesn't matter But if we know these velocities, we can understand everything. If I know velocity v1i, 2f, then I can calculate momentum initial, right? This is a vector, we know mass m1, v1i, plus mass m2, v2i. Then similarly, I can find momentum final, mass m1, v1f, plus mass m2, v2f. By knowing these two, I can check whether the momentum is conserved or not. Now, when this collision happens, if I can get rid of the friction, friction is the only possible force which can apply there. There's no any applied forces. If I can get rid of the friction, then I can find the condition called net external forces are zero. If net external forces are zero during the collision, then this should be definitely equal to zero. Momentum must be conserved. So I can check that. That is a conservation law number one. We can check that. We just need to know velocities, and also we need to make sure friction is zero, right? If we're doing this in class setting, what we're going to use an item called the air track. So what is the air track is does? It's a very simple very simple apparatus. I think I mentioned this some time ago too. We have a solid beam, which is a three-dimensional like the aluminium beam. Inside is hollow. So what we're going to do by using the compressor, we can actually provide the airflow to this beam. Inside this hollow air going to go into this direction. And at the same time, this beam actually, this is a three-dimensional hollow object. So it has these small dots on the surface. So what it does, when the air goes on, the compressor have the high pressure. As a result, air will come out from these small dots. So when it is come out, if you place a small cart on top of that, that cart will actually float. So that cart will float. This space in between the cart and the air track going to be very small. Okay, this is maybe like 0.2 millimeters, something like that. Extremely small, but that doesn't matter. As far as the surfaces are not touching, then we don't have any friction. So we can easily avoid the friction by using the air track. In today's experiment, we not the real experiment, but in the simulator, they simulate exactly that way. There's air track, and then there's no friction. Basically, there's no external forces. As a result, object will move on this air track with constant velocity. Like for example, if I have a cart here, if there's no friction, if you just give a small push to this cart, this side, just like by using the finger, if you tap it, then this cart is starting to move this direction with some initial velocity. Cart number one, velocity 1 before collision I. Then if I have another cart here, then those two will collide. Then after collision, it will either go in the same direction, maybe bounce back, doesn't matter. All we're interested in is finding those velocities, right? Any question? Okay, now when it comes to the velocity, how are we going to measure the velocity? So because we're interested only velocity, because if I know velocity, everything we can calculate, right? Momentum is depending on the velocity, and also energy depend on the velocity. In this case, in terms of energy, we're interested only kinetic energy, right? So when we go to the kinetic energy is always half mv square. So still I need the velocity, right? So that's the important part. Now how to find the velocity? If I have an air track, if the cart is moving, let's say I have a cart right here, cart length is, let's say d1, and the cart moving this direction with some velocity v1, I want to find that. Now what we're going to do, we're going to take the photogate. What the photogate does, photogate. So the photogate has like U shape, this kind of, this is the photogate generally. Photogates have this U type. A plastic is the piece, but that plastic piece, that this is actually connected to the timer, electronic timer. when you switch on the timer and then put it into the gate mode, what it can do, it can have a different mode depending on the type of photo gate we use. Generally, this has a small 2 dots right here. So what it does, it actually have a IR coming through this 2 dots. It go from one dot to the other. As far as that light ray is actually continuous to the other end, this is actually have a complete loop. So it has a complete loop. As far as the loop is completed, timer will not switch on. There's a timer, but timer going to be off as far as this loop is actually completed by this ray is going from one end to the other end, let's say A to B. Now what we're going to do, we have a cart right here. We're going to let that cart pass through exactly this location, exactly in between that U-shaped photo gate. When the cart is in there, what will happen? Loop is on the off position. Loop is not completed. As a result of that, timer will switch on. When the timer will switch on, right here we have a scale. We can read actually timer doing the, it can give actually very accurate reading down to about like 4 decimal places in unit seconds. So it really accurate below the millisecond level. Okay? And we can find the time, how much time it actually took this amount of distance to pass through the photo gate. So this T1 going to be that time. So which means I can find velocity V1I is simply the distance or the length of the length of the cart divided by timer given by the photo gate. I can put I there before the collision, for example. So that's what we're doing if this is an in-class experiment. We have a AR track, and then we have 2 carts right here. Then we're going to set up the photo gate 1, let the cars pass through that, find the initial velocity. After that, cart will be collide. After that, we have another 1 or 2 photo gate after that. Then we can find the collision. So usual in-class setting actually, in our experiment, this photo gate can read more than one time at a time. So if there's 2 cars passing through within like, let's say 1 second period in between them, it can record both times. But in the simulator, you can see the different photo gate for each case. But because that's a simulator, but in the real life scenario, we're not going to have that many photo gate. It's going to be 1 or 2 photo gate per setup. Okay, question. That's all. Then after we figure out the velocity, then we going backward and then figure out the concept of momentum conservation. Then you go back right here and then figure out energy conservation. By checking the energy conservation, we can understand the type of collision, for example, whether the type of collision is elastic or inelastic, and then so on. So that's the plan for the experiment. Okay, only important thing to measure is that time. Okay, so that's the only variable, and the length of the cards, and also we need the mass of the card. But those are we measuring only once. The time we have to measure depending on the collision. Okay, we're going to study different type of collisions. Okay, question. All right, then let's continue to the simulator. And in all of these equation, you will see again in this week class. So at this point, we are not interested in anything calculating in terms of other than understanding the concept of the conservation laws. Okay, that's our main focus right now. You can click on the simulator. That will bring you to the simulator page. A very simple simulator. Okay, so that should be look like this. Okay, and then if you take a look the simulator, and also the you can take a look the data tables too. If you take the data tables, there's only I think 3 or 4 data tables, only 3 data tables. That's it. There's no graphs or anything, but it needs a lot of calculation. Okay, since we using the Excel to calculate, it will be a little bit easier because if you do one row, then we can click and drag technically. But the table number one, all we have to do separately each calculation because that's the data part. And then table number two, we investigate in the conservation of momentum. Table number three, we investigating conservation of energy. Okay, that's the plan. So which means the table number one is the critical. Anything wrong there, next two tables will be inaccurate, right? So we have to be very careful with table number one. When it comes to table number one, what we investigating is the velocities of the objects before and after collision. Now to do that, we need to measure only time, right? So we have to measure the time before the collision passing through the photogate and after collision passing through the photogate, right? We have those numbers, then it's a very simple calculation to do. Now, if you look at the simulator on the other hand, now you can see the air track, that the gray color horizontal line is the air track. And there's a pink color small object, that's a cart one, let's say smaller cart. If you're doing this in-person class setting, we have exactly same kind of setup. And then we have a smaller cart and the larger cart. The smaller cart and the green one is a large cart. And step number one, I need the length of these cards, right? You can click this card and then put it inside here. That's a vernier caliper, then that will give you a number, right? That's the length of the card. So those information, let's put it into here. Put those information into here. Card number one. Length of the card number one, it's about 8.25 centimeters, but I need the unit of meter, right? So this should be then 0.825 meters. And let's measure mass of the card. You can click and drag the same card and then put it on top of this balance. That's how exactly we're going to be measuring this. If it is an in-person setting, only difference is that in-person setting, our is called, we don't have actual electronic balance in physics labs. We have a different type of balance, which is accurate actually, even accurate than this one. It can go down to 0.01 gram, right? Now this can go down to only 0.1 gram. So even accurate than this one, but it's gonna take a lot of time to measure because that's a manual balance. It's not electronic. There's no scaler like this one to display anything. So you have to do that measurement very carefully. Usually take a fair amount of time. Okay, so the mass of the object is 193.7 grams, but I need that in kilogram, 0.1937 kilogram because divide by 1000, right? So I have those information. You can bring back the cart here. Then cart number two, put it inside the vernier caliper. That will tell you the length of the card number two, which is 22.25, which means 0.2225 in meters. Let's measure the mass and then place on top of this mass scale. Then it will tell you the number 481.1, which means 0.4811, and it's in kilogram. Okay, question. All right, that's it. Then now the idea is that we're gonna try to produce different type of collisions, right? So that's the plan. So now when you come to the collision, there's two types, right? Basically, one is elastic, one is inelastic. But there can be collision in between too, right? There are collision, elastic means there's no energy loss at all. Perfectly inelastic means the after collision, two objects are actually combined into a one object. So those are the type of collision what we call perfect inelastic type collision. Before we have two objects, before the collision, after one object can go into the other object, for example, or connect them together, those type of collision is called the perfect inelastic. And then there are in between, like we can generally say partially elastic. That's what actually this first row, first column tells you. You can see elastic, cards moving in the same direction, elastic, card moving in opposite direction, elastic, one card is at rest. So we can do three different investigations. Send in the cards same direction before collision, send in the cards opposite direction before the collision, or keeping one card at rest and then send in the other cards, right? That's what actually this tree means. And the same I can do for inelastic, and then same I can do for partial elastic. So what we're doing, we actually investigating three different cases for each type of collision. Okay? That's what we're doing, then totally 9 different cases. Now, if we try to do this much information, this much things in our in-person setting, definitely we don't have enough time. But since we're doing with the simulator, it's a very simple. Okay? It's going to take only half an hour to collect the data. Rest is just the calculation. Any question? Okay, then let's start. Now all we have to do now, if you go into the simulator, a couple of things you can see. On very top, you will see the card direction. So we can keep the same direction, right? I need to start with the elastic type, same direction. And the next one is inelastic. If you click on that, you can change that into elastic because first we try to understand the elastic. Okay. And then just below that, you see three different type of options. Start cards, reset cards, new experiment. Don't click the new experiment due to any reason during the experiment. Okay. The reason, even after I done the first one, if I want to go into the second one, you should click only reset cards. If you click the new experiment, what it does, it actually make the completely resetting this whole page. As a result, mass and length will be changed. So that is not good because mass and change we assuming stay constant throughout the different type of collisions, because otherwise we cannot compare and then understand this behavior, right? In class setting, we know we're not going to get different length or different masses for each time. Okay, make sure you never click the new experiment, and that's it. Then it's a very simple. To make sure, I'm going to just recheck this very quickly in case if I did click new experiment due to any reason. This is going to be very bad calculation. Okay, all are good. You can click the reset card always. All I have to do now, click start cards. You can see the green one moves slowly, pink one followed by that, but its velocity is higher. As a result, pink one collide with the green one. After collision, you can recheck that. You can see after collision, green one is moving faster now. Pink one becomes much slower, but there's no direct attachment between them, okay? Because we investigated now perfectly inelastic type collision. There's no energy lost at all. Okay, now we have all the times. Now this is easy because you have 4 different photo gates, and then each photo gate telling you what we actually measure. So we know photo gate 1, pink color line, it even tells you the direction of motion. That's important because all the velocities are actually vectors. So when I calculate in the velocity here, we have to put the vector sign. We're not going to put ijk or anything because then we can't really do that calculation with the function here. But the positive negative sign is important because we know all the vectors are on x-axis. You don't need to put ijk anything there. But sometime after collision, card can bounce back. If that happens, we should report that as a negative number. We know rightward direction to your right hand is our generally standard positive x-axis, and the leftward direction in your left hand direction, general negative x-axis. We have to report those things accordingly because the momentum in table number 2 is actually a vector. Okay. All right. Any question? Then let's continue. That's very simple calculation. We can report first the time, then let's do how to do the calculation in a bit. Time going to be always unit second, right? Unit second. And then the velocity going to be always unit meter per second. All right, then the time for case number 1, elastic type collision, cart moving in the same direction. Before the collision, cart number 1, pink one, time for that 0.25. Cart number 2, green, first arrow, first photo gate, 1.44. If the time is higher, which means object is moving slower, right? Velocity is lower. Then after collision, you can see pink one, 1.04. You can see the pink one becomes very, very slow after collision. Green one, on the other hand, compared to the before collision, it becomes fast. That's expressed by the time values. Okay, if you take more time to pass through that photo gate, which means you're moving slower. Right? That's the idea. If it is moving faster, you need a small time to pass through the photo gate. Question. That's it. Then you calculate this one. Very simple calculation. So to do the calculation, what we do, velocity v1i equal sign. We know velocity cart 1 initial. Cart 1 distance is 0.0825. Sorry, 0.0825 actually. 0.0825 divided by time for the cart 1 before the collision, cell value C13. Enter, that will do the calculation. And the velocity cart number 2 before the collision, cart number 2 length 0.2225 divided by time before the collision, cell number D13. And equal sign cart number 1, 0.0825 divided by after collision cart number 1, cell number E13, equal sign cart number 2, 0.2225 divided by time value after collision, cell number F13. So you have velocity calculated. Now you look at the velocities, then you will see what happened, right? So the cart number 1 initially moving much faster, but that velocity decreased by large. So that because during the collision, momentum changes of the object. However, total momentum of the system must remain constant. Okay, that's what we're investigating. Momentum of each object can change individually. But if you add momentum change of every object in the collision, that number remaining constant. Okay? And on the other hand, if you look at the object number 2, initially moving very slower, after collision, it moving fast. Okay, any question? All right, then that's it. Then we have to do just simply re-investigating this condition by changing the way how we send in the cards, right? So instead of cards sending the same direction, we can send the card opposite direction, for example, case 2. So to do that, you have to click on the reset cards in the middle. Don't click the new experiment due to any reason. That will change the length and masses. Then there's no meaning comparing the momentum later case at all. All right, then again the same thing. All I have to do, I'm going to keep the elastic condition, but the card direction, let's change into opposite direction motion. Now you can see green going to start at the far right end, the pink going to start at the far left end. That's all. Then click start cards. You can see cards is head-on collide now. You can see after collision, it now bounces back. Now in this scenario, you see two velocities are negative, two of them are positive. So that's that kind of collision, that direction is so critical in table number 2. Table number 3, it doesn't matter because it's kinetic energy. Kinetic energy always a positive number because kinetic energy is velocity to the power 2, right? But momentum is mass times the velocity. So when we do the momentum conservation, we adding all the momentum together. We have to add them as a vector. As a vector means anything go opposite direction has to have a negative sign. Otherwise, you will not going to see momentum conservation correctly. Okay. Now let's record the numbers. So what we have, cart number 1 before the collision, pink arrow number 1, photo gate 1, right? 0.21. Card number 2 before the collision, green arrow, photo gate number 4, 2.28, but that is negative. There's no meaning putting the negative sign to the time. You can if you want to, nothing wrong, but we will put that negative sign after we calculate the velocities. Okay. And the cart number 1 after collision, pink arrow, photo gate number 2, 0.27. Card number 2 after collision, green arrow, photo gate number 3, 1.1. Let's do the velocity calculation. That's so simple. You can just click and drag this because it's the same kind of calculation, right? It's nothing much to do. Just click and drag. Okay, now two velocities are negative. Now that is not representing still, right? See, all of them are positive. Now that I have to correct, which means cart number 2 velocity initial must be negative. You can multiply this calculated value by -1. Then it will give you the negative sign automatically. And also cart number 1 after collision must be negative. You can multiply this also by -1. So it will become negative. That negative sign is actually very important. Okay, if we don't have that correctly, then next table number 2 going to be very, very negative. Okay, equation. All right, then let's continue. Let's take a look the elastic type collision, but let's keep the one cart at rest. To do that, you can reset the carts and then change the cart's direction into one cart at the stationary. Then you will see cart number 1 is now at the stationary. Cart number 2, green one, is at the stationary. After we start, you will see cart number 1 will move. And then after collision, both carts will move. Let's start the cards. You can see green one was at stationary, but after collision, you have seen what happened. So let's check this again. After collision, you can see green moves to the right, but the pink actually bounced back, right? So because of that, the pink after collision is actually a negative number. Let's record the data. Before collision, card number 1, 0.27. Before collision, card number 2, which is at rest, which means time I'm going to put 0 there, but that 0 has no any meaning because the reason I can't divide by 0 anything to get the velocity, right? If you divide the distance by 0, that will give you a wrong answer. So I'm going to just write here at rest. Then the card number 1 after collision moving backward, time is 0.64. And then card number 2 after collision moving rightward, time is 1.28. Do the calculation again, click and drag. But you can see this cell right here, say wrong answer there because I have rest here. I can't use that to do any calculation, but we know that must be 0, right? Card number 2 before the collision, it's not moving, it's at rest. You have to put the 0 there yourself. Okay? Manually, you have to add the 0 there. And also, if you look at the card number 1 after collision, moving backward, bouncing back, that should be a negative number. So that right here has it correctly because the previous cell has that negative sign. Okay, now it's fine. Question. Okay, then let's continue. It's that simple, right? It's a extremely simple experiment, but if you do this in class setting to complete this view, gonna take like almost 1 hour or maybe even more than you can, because there's so many problems if it is a real experiment setup. With the photo gate, you have to reset the photo gate every time and then make sure you're reading it correctly. And in class setting, we don't have this many photo gate. Each photo gate actually reporting 2 time values before and after collision. So that we have to get it carefully by using the photo gate menu bar. So that those things going to take a lot of time. So, okay, any question? Okay, then let's continue. Let's take a look in inelastic type collision. So the earlier I mentioned inelastic type collision is the after collision two objects can combine into a single object. So that type of collision generally called perfectly inelastic type collision. Okay. Let's take a look now. If I want to do the inelastic collision, I can reset the cards, change the collision behavior into inelastic. Let's do again 3 different type of inelastic by sending the card same direction, by sending the card opposite direction, and then by keeping the one card active. That's the plan. So already inelastic, same direction, our next case. Start the cards. You can see both cards move initially. After collide, let's reset and then do it again. After collide, you can see 2 cards connect together, okay, as a single card. Now it's moving as a single object after collision, okay. So let's record the data before the collision. Card number 1.24 positive, card number 2 1.91, and then after collision there's no 2 objects now, it's a 1 object. What this photo gate is actually telling you the time for the total length, not for the one length of the object. Okay. So if it is in class setting, we can actually see 2 times there, because in between you can see little bit of gap. So if it is a gap there, actually photo gate switch off and then switch on again. Because of that, if it is in-person setting, you can actually see 2 time values recorded in that photo gate. But the simulator giving us only 1, so that time is actually for the total time. So because of that, what we're going to do, we're going to merge these 2 cells, because I don't have now 2 cards. I have only 1 card after collision. You can merge this cell, 2 cells together. That merge is you can find on the home alignment settings. You can see the merge and center. You click on that, it will merge automatically. So which means after collision 1.67, that time is actually for the both. Question. Okay, then let's continue. Now let's calculate the velocities. First 2 before the collision you can calculate. Click and drag, that should be fine. However, after collision, I can't click and drag because now there's no 2 cards. Okay, I have 1 card. So I'm going to merge these 2 cells again. And then after we merge, let's do the calculation manually. Equal sign, parentheses. Length, I need the both cards adding together. Right? Length of card 1.0825 plus length of card 2.2225. Close brackets. Divide by time of that total length E16. Then we have the right answer. All the direction is fine. Make sure that negative sign, these 3 cells. That's extremely important for next table. Okay. You need to make sure you have those signs correctly reported. If anything wrong there, for the next calculation. Any question?
Can you just show the equation for the last one more time?
Oh, yeah. This one. Add the formulas here. I completely forgot that this is velocity final. Okay. That's the function which I use after velocity final. I think the previous ones are very simple. To make sure, let's add those for at least for one of these. 1i. 2i, and it's the same thing. I'm gonna add only these two. 1f. And then v2f. Okay. So okay, now those are the commands which we used earlier. You have to collect them as you progress through the tables. Okay, you don't need to repeat the same calculation again and again as a function in the table, the appendix C, but every different function, make sure you add them. Okay. All right, any other question? All right, then let's continue. So we just need to repeat the inelastic collisions, right? I have to repeat 2 more times to understand how it changes as a function of how the cards are organized initially before the collision. Okay. Now let's do reset cards, inelastic collision, but change the direction of motion into opposite. Let's start the cards. You can see now it's going to be head-on collision, but the cards are combined afterwards. You can see now it's moving like a single object, right? That arrow, this photogate number 2, arrow has a both color, so which means that the cards are now combined. Okay, it will give you the total time for the both cards. Let's record the numbers then before the collision card 1.20, before the collision card 2.03. However, velocity must be negative. We have to make sure we're going to add that correctly, the negative sign. After collision, we have only one card, one object. Both cards together are going to merge that cell. And then time is 7.78. It's moving very slowly, okay? You can click and drag this now because it will do the calculation correctly. Because I merge these two cells and these two cells, this one merge will merge automatically. Only one correction we have to do is actually for this guy, because card number 2 before collision v2i must be negative, right? So I need to multiply this number by negative sign. Why is not showing me the function? None of this showing me the. Oh, I know. This also I have to do the calculation because you remember there was a mistake on previous cell. Okay, I'm sorry. So that's very important because right here we add the 0 purposely because of that this cell right here did not do the calculation correctly. You have to correct it. Okay, which means card number 2 before the collision equals sign length of the card number 2.2225 divide by time before the collision, D16. Please correct that after, otherwise you will not get the right answer. Okay, then you can click and drag. Now it's fine. because all these velocity numbers should be very small, like 0.3, 0.2, 0.1, things like that. You should not get anything larger than 1 at all, because in this simulator, the velocity are very small. Make sure you correct this one, because this particular cell, we actually purposely adding 0 there, that cell, green color cell. Because of that, the cell underneath, if you click and drag, doesn't have a right calculation. Calculation is same as the cell number H14, for example, but you have to really do it again. Okay. Question. And also, card number 2 before collision should be negative. So I have to multiply this 0.11 cell value H17 by -1. Then only I have the correct sign attached to that. Okay. Any question? Okay, then let's continue. That's all we have to do. Reset cards, keep the inelastic type, but change the cards into one, stay at rest in the middle. With that, then let's click the start cards again. You can see now card 2 was at rest, but after collision it becomes as a single object and then moving together. That's all. Then the card number 1 before collision 0.22. Card number 2 before collision is stay at rest. I'm going to just type the term rest. And then after collision, I don't have one card separated. I have only single object. I'm going to merge these two together. Total time 2.81. Now these two you can click and drag. This cell right here, you have to type 0 yourself because it's an invalid cell. Now I will highlight this also in a different color to represent those are the items you can't click and drag. Those are the places you have to manually adjust values accordingly. Especially the velocity you have to put manually 0. Okay, question. Okay, then let's continue. So we are left with only other type of collision. We can go either fully elastic or fully perfectly inelastic, or we can do in between, like partially elastic. Maybe it's gonna losing little bit of energy, but not much. We can understand that 3 type of collision easily in table number 3 by looking at how the energy loss in table number 3, you can actually clearly identify what are these type of collisions are. Okay. So to create that, let's click the reset cards. Change the inelastic, the collision behavior into partially elastic. And then change the direction into same direction. And then start the card motion. Start cards. You can see card number 1 comes very faster, collide. And now it's moving extremely slower. After collision completed, let's record the data. Card number 1 before the collision, 0.20. Card number 2 before the collision, 2.85. It's moving very slowly. Card number 1 after collision, 2.13. It start moving very slowly. Card number 2 after collision, it start moving faster, 0.97. Now, I can't click and drag any of these 3, okay? You have to really do that calculation. So all of those, I have to redo the calculation because these cells doesn't have the right way done. like these three. So we have to do it again, equal sign. Length of the card number 2.2225 divide by time for the card number 2 before collision, cell value D19. Card number 1, length of that 0.0825 divide by time for the card number 1 after collision, cell value E19. Card number 2, length 0.2225 divide by card number 2 after collision, cell value F90. Those three, all these green cells are the manual cells you have to redo again and again. And also these points you have to redo. All the rest you can click and drag previous cells, then it will do the calculation correctly. Okay? But any of these green color cell, if you do calculation by click and drag, then you have a wrong answer. Okay. All right, question. Okay, then let's continue. Let's do partially elastic but card moving opposite direction. So let's reset, change the card direction into opposite, start the cards, and see it's going to be a head-on collision, right? There you go. So the card number 1 is small, but it's moving really fast. It carries the huge momentum. That's why even it's a small card, it can actually move the card 2 backward, because the mass is smaller, but the velocity is larger, momentum is higher. Record the time values. Card number 1 before collision 0.20, card number 2 before collision 3.98, and it's negative, so we have to put that negative sign later. Card number 2 after collision 0.54 negative, card number 2 after collision 1.28. Now this you can click and drag, that will do the job, because it's very similar, but I'm going to get rid of this color there. All right, now I have to put the sign correctly. Card number 1 before collision must be negative. This should be multiplied by negative sign. And card number 2 after collision must be, card number 1 after collision must be negative. This should be multiplied by negative 1. Everything else is fine, okay? Here I have 3 negative signs. Let's put some different color there. And here I have a couple of negative signs again, okay? All right, question. Okay, then let's continue. So the last one, let's change, reset the cards, change this into one card stay at rest, stationary. Click start cards. After the collision, card 1 bounce back. Now let's record the data before collision, card 1.20. Before the collision, card 2 is at rest. I'm going to just type that term. After collision, card number 1, 1.06, but it's negative. We'll put that negative sign for the velocity. Card number 2 after collision, 1.12. We can click and drag, however, we have to do a little bit of adjustment. First get rid of that color actually, okay. And this one should be 0 because card 1 before collision is there at rest. Card 2 after collision bouncing back, that's negative, that's correct. Okay, question. All right, now all we have to do is actually investigate the momentum conservation and the energy conservation. Now, to do that, we have to do the momentum calculation. Now, the earlier we discussed very in detail what type of calculation we are looking into. Right. So in terms of experiment, we done in the experiment, right? Rest is just the calculation. Even this is an in-class experiment. That's all. After you collect that time values, then technically the experiment done. But to collect the time values in class setting, taking a lot of time. There are other lot of technical problems if it is in class setting. Now we discussed earlier, there's two type of collision. Doesn't matter what type of collision because of the Newton version of the momentum law. Newton version of the momentum is actually tell you momentum is actually conserved if the net force is zero, external force acting on the objects. Okay, if I look at the collision carefully, I understand that during the collision there are internal forces, but those internal forces will cancel out if I add everything together in one direction, right? Like in the Newton laws we usually do. Because of that, if I assume there's no friction or there's no any other forces during the collision, then momentum must be conserved, right? So that later on Wednesday, we will talk. We will take a look this very in detail. Then you will figure out then this part right here. If the momentum is not conserved, so which means, let's say in this particular lab, we should not get momentum not conservation at all, right? Because all the cases we studying here, external force is actually zero. Momentum must conserve. Delta P must be zero. But there can be cases if delta P is not zero, then what it tells you, there should be a net external forces. So which means if external is actually delta P over delta T, which means I can simply say delta P is actually simply equal force times the delta T. This part right here, that force times the delta T is actually what we call the impulse. What will happen during the collision? There can be a force acting on the object, but that force can be rapidly acting and then disappear immediately. So the very quick force, like within like few milliseconds, it appears and disappears. So which means if I can find the delta P, if the delta P is not zero, then the momentum is not conserved. That's one thing. Then the external forces can appear. On the other hand, if I can find the delta P as a number, so that we can use to understand what will be the impulse acting during the collision. Okay, there's a lot of different type of calculation we can do. So I think this is a good experiment we're doing before the class work done. You have to have a fairly good understanding by now Wednesday, because all of these scenarios we actually doing again. Not all these 9, okay? Some of them. At least 2 or 3 different cases. Very in detail we will do the calculation. All right, so any question? Okay, then let's continue. Let's go to table number 2 and then we'll start calculating momentum. So when it comes to the momentum, let's take a look the momentum units, right? So the momentum is you writing mass times the velocity, right? In terms of unit, mass is measured in kilogram, velocity is measured in m over meter per second. As a result, kilogram meter per second. However, it has another unit, right? Because if you go here, the Newton second law, but the momentum version. Now, Newton second law has a 2 version, remember, okay? The general version is mass times the acceleration, but there's a second version, rate of change of momentum, okay? Now, if I go that, then the changing momentum is actually just simply the force times the time. So the force is Newton, time is second. So that's also the unit of momentum. Let's take a look at that units very quickly, because that unit should be equal to this guy, right? So this unit should be equal to kilogram meter per second. So To do that, you know, Newton is MA. So which means Newton should have to have a kilogram. Acceleration is meter per second squared multiplied by second. One of the second cancels out. You will get the unit of kilogram meter per second. So which means these two units are actually the same. You can either write Newton second or kilogram meter per second. Doesn't matter. Question. Okay, then let's continue. Momentum before the collision. I can write either Newton second or basic unit. I'm going to write the base unit here because this is the first time we discussing this. But later in the classwork, you can write the other version of the units in terms of Newton second. Okay, doesn't matter. Changing momentum as a units too, and then these two tables, table number 2 and 3, you can see another column here, right? Column number this 1, 2, 3, 4, fifth column. So the fifth column we are not completing during the class. In terms of data table submission tonight, you don't need to complete the column, this last column in terms of data table. Okay, but you have to complete that for the lab report next week. That asking whether you observe the momentum conservation for each case or not. If not, you have to explain why. If yes, you just need to say yes, we observe the momentum conservation. If not, you have to write it down why. I already gave you a couple of ideas, the scenarios where the momentum not conservation happen, and there are other cases is possible. Let me give you that information because that's important. In this AR track, there are a couple of other scenarios can happen. We assume U is 0, right? But technically, it may not be 0. The reason AR track is look like that, it's actually huge cylinder. It has a dot. A lot of this is small dots on top of that. So the air is actually flowing outward very rapidly. Now you place a cart on top of that. All of these are metal, okay? We assume metal to metal, there's no touch. There's not touching metal to metal. However, airflow is actually rapidly flowing away from the side. As a result of that, if you carefully observe, what you have is the cart bottom surface and the flow of air going one way or the other way. So the air is actually flowing very rapidly. That air flow, which is actually goes under fluid dynamics, which is the first lesson you will be we will be learning on 290 class, physics 2 class, first lesson. But that is only our college. We do that class, that chapter with the physics 2 class. Generally, that chapter is part of this class. In every other college, technically, as I know, some colleges they don't do that class at all for the general. So what is happening is actually since the air is rapidly moving with that surface, if you look at it carefully, this bottom surface right here, the very bottom of the cart surface, the air molecules is actually very attached to the cart surface, right? That air molecules. And then other molecules, not that much attached. Those are moving rapidly. Because of that, you have some sort of still little bit of air friction. Because of that, even we assume the friction is 0, it may not be exactly 0. It may be like very small number, but 0.01, 0.005, things like that. But still, that will be considerable effect, okay, to produce a force. And one other scenario which can happen during this experiment, this air track should be very level. Air track should be very level, which means they should be on exactly horizontal x-axis. If you're doing this in class, then we have actually 2 or 3 legs attached to this. Then there's a way we can actually change that length. Because of that, it's very difficult to level. We usually place the level right here and then try to level it, but generally you can't get the perfect level. Just eyeballing it. Because of that very small, very slight change, like maybe like 0.002 degree of angle, slight angle relative to x-axis, positive or negative, doesn't matter, will create another type of force. So because of that, in class setting, this will be a huge problem, but this is not a problem for this simulator, okay? Simulator, this should not be a problem at all. Simulator, the problem may be they can include this scenario a little bit. They assume mu is 0, but it may not be directly. And the other cases we discussed earlier, a few other possibilities are. And those are the things you have to explain here, okay? Not very detailed, like, huge paragraph, just 1 or 2 sentences enough for each case. Okay, question. All right, so let's take a quick break and then we'll, this calculation going to take very little bit of time, maybe half an hour maximum. And then after the break, we'll finish the lab and then start next chapter. Okay. Okay, so let's continue. All right, now you have a good idea what we're trying to do on table 2. So let's calculate. So momentum initials, so which means I have to add the moment. If you have more than one object, we have to add momentum of each object, right? So in this case, we have 2 objects, mass times the velocity for both objects. Separately, we have to multiply and then add. So let's do that. So the equal sign, momentum before collision, brackets, mass of the object number 1. Mass of the object number 1 is 0.1937. 0.1937 multiplied by velocity of the object number 1 before collision, okay? Case 1 before collision, cell value G13. Cell value G13, close brackets, plus parentheses, mass of the object number 2, 0.4811 multiplied by velocity of the object number 2 before collision, cell value H13, close brackets. Hit enter. Okay, we have the momentum there. And then let's do the momentum final. Let me copy paste that function right here. So this is momentum. I means total momentum initial. Okay, this is going to be M1 V1I plus M2 V2I. Okay. All right, so let's do momentum final. So the same way, but the slightly different because I have to use the final velocities. So the mass of the object number 1, 0.1937 multiplied by velocity after collision object number 1, cell value I13, close bracket, plus open brackets, mass of the object 2, 0.4811 multiplied by velocity of the object 2 after collision, cell number J13, close brackets, hit enter. They're exactly the same. That's what we're expecting. Momentum must be conserved, right? So the however, I would like to check at least a couple of decimal places more, right? So these are calculated values. Let's do that for the velocities also. All these velocities are actually calculated values, right? So let's do 1 decimal place more. Highlight that area. You can format those cells to 1 decimal place more. Highlight, right click, format cells, number, and then increase decimal places into 3. Because I want to check whether momentum is really conserved or maybe there's a different at least second or third decimal level. Okay, so let's reformat this whole table also to about right click, format cells at least 3 decimal places. Okay, still the same. So I want to check that into 4 decimal place. See whether it is still the same. There's very slight difference on 4 decimal. So that's good. That's not bad actually. That's good because we know we expecting momentum conservation. That's true. But however, there's the huge chance in this kind of experiment, momentum may not be exactly conserved. You will see very slight difference. We discuss many different cases how that can happen in real life experiment. You can write 1 or 2 sentences accordingly. Okay?
Professor,
Yeah.
I have 2 different values. Did I do something wrong?
Yeah, if you have 2 different values here, you completely doing something wrong. Definitely, you have to recheck this function. Okay, that's all you have to do. Just recheck the function. So it should be exactly look like this, but maybe either some parentheses missing, or maybe you selecting the different velocity. I don't know what's wrong is, but definitely there's something wrong. It's going to be V1 final, and then this going to be V1 final, V2 final. Check the function very carefully, okay? Any other question?
You want 4 decimal places, right?
Yeah.
Okay.
Yeah.
Does
So
it same or not?
all 4 are same.
I have 0.1209 and 0.1213.
Okay, it's very little bit different. That's okay.
Okay. Thank you.
Yep. That's fine. It's very slight different. You can see it's almost like no difference at all, right? If I rounded into 2 or 3 decimal places, you're not going to see that difference at all in terms of significant figures, right? But for this lab, we are more interested in the accuracy of these conservation laws, not really the significant figure. So I would like to keep 1 or 2 decimal places more. Then that will help you to think about a little bit more, as we discussed earlier, what are the possible cases this momentum can be still not conserved. It must be conserved, but if you observing not, then you can write up 1 or 2 sentences. That will help you to better understand actually this chapter. Okay, anyone else has any question? Yeah.
I rechecked the final velocity of the like mass 1 and 2 to calculate the total momentum and the total momentum after the collision, and I still have different answers.
Then something is wrong. I don't know what is wrong is. The only way to check, make sure these are correctly done. You need to check that first. When you're calculating the velocities, you know you have to put the right length of the each cart. Okay. If you mix that up, then these numbers may not be accurate. What you done here, right? If that is not accurate, then everything gonna be inaccurate. So you need to first check that. When I do V1i, it should be length of the cart number 1. And when I do V2, it should be length of the cart 2, time of the cart 2. So check those things first, okay? And if those are correct, then right here, only possibility can go wrong is just this function. So if the function is correct, table number 2, I don't know what else can go wrong. Technically, nothing else can go wrong. Anyone else has any problems? Okay, so I don't know why few of you guys getting different answers. Those are the places you need to check, okay? Check that out. Should be, you can figure that out. If not, we can take a look after the class, okay? All right, any other questions? Okay, let's check the not the percentage error. We could do that too. We can compare these two, but let's check directly the change of momentum, equal sign. We just interested just the number. Okay, I'm going to use ABS to absolute value equal sign, difference between final minus initial. And you can see it's a very small number, almost no change at all. But if still there's a little bit change, you can just write up why that small change is there. In this case, it may be the rounding error too, right? So because the timing, time values is given, and that's one other error actually for particularly this one. So it may be the timing error, rounding error too, because time is given only down to 2 decimal places. But we are actually, after calculating, we are checking 4 decimal places. That means almost twice the accuracy of the given time values. So that may be the one error too. If we rounded into 2, then definitely there's no error at all. So this is not any experimental error, technically just maybe the rounding error we see here. It's not really big number at all. Okay, question. Guys had the problem earlier, the figure out, or you guys has still the same issues?
I have a 0.013 difference. Is that too big?
0.013, no, that's very large, right? You have a change in second decimal place level.
Yes.
Yeah, that's still large, I think. It can't be that large. It should be very, very small, because the energy you will get that such large values, because energy is not conserved in some cases, but the momentum we should not get such large values, because momentum is really, really should be small if there's a change. But if you do in-person setting, definitely we're getting such large values, fairly considerably large values. Okay, question. Anyone else has the same kind of issues?
Professor,
Yeah.
is it fine if it's 0.0017?
Yeah, that should be fine, I think. Third or fourth decimal level is okay.
Okay, then.
But yeah. But if you have a second decimal place error, you may need to take a look again. The places to look is first here. Not just the numbers, okay? You have to go and click on that cell, make sure you do the right calculation. When you do V1I, it should be length of the cart 1 divided by the time of the cart 1 before collision. Likewise, you have to investigate all four these cells, okay? If you do that and then make sure those are correct, then take a look at the function. Then the rest is first 3 cases, all of these elastic cases, I can just click and drag, right? So you can see if I click and drag, it will do the calculation automatically. I think the third decimal place is fine. I'm also getting 1.0016 for the second one, momentum change, and the third one again, fourth decimal place. So which means third to fourth level, okay, accuracy wise. This is probably the rounding error, nothing else, but that's fine, I think. Not exactly the rounding error. There's a good point here, actually. You can take a look. This is elastic collision and head-on, right? So these two, you can see this is before the collision, 0.291. This is actually 0.308. That's not exactly the rounding error. If I go to the second decimal place, yes, rounding error, I can say. But if I look at the third and fourth level, the accuracy of the decimal places, it may not be the rounding error. So which means you have to explain what are other possibilities are. You can't just say rounding error at all. I would suggest to write it down 1 or 2 sentences with the comments we discussed earlier. There are other cases, other possibilities. The momentum cannot be conserved because of mu may not be 0 because of that external force applied on during the collision. That may be one reason. And then so on. Okay, question. So this column I will let you guys to write, okay? And then no need to complete that before submitting the data sheet today, but you have to complete that in terms of lab report. Okay, now you can see these labs are much easier because after we complete the tree tables, there's no graphs or anything. You just do the lab report, okay? All right, so let's take a look the inelastic collisions. Again, the same kind of work we're doing, right? Equal sign, parentheses, momentum before the collision, total momentum. Mass of the object 1.1937 multiplied by velocity before the collision object 1. I'm on now inelastic, cart moving same direction, column 16, okay. Cell value G16, close brackets, plus open brackets, mass of the object number 2, 0.4811 multiplied by, and the velocity of the object number 2 before collision, cell value h16, close brackets. Hit enter, so I got the momentum for that. Let's do momentum. Let me copy paste that same command. Right? There's nothing new to actually copy paste, but let me copy paste that again. This one I'm going to get rid of. This one will add that. Yeah. All right. So let's see momentum final for that case. Equal sign, parentheses. Now the after collision for this case, the objects are combining together, right? Because of that, I have to add the mass together. Mass of the object number 1, 0.1937 plus mass of the object 2, 0.4811, close brackets, multiplied by, then the velocity is single, right? Single velocity for both. So that is cell value now I16. Hit enter. You can see still very close by, only the third decimal place is the difference. Okay, let me copy paste that function true. And this command also I need to edit. Parentheses M1 plus M2. Times V2F. We should say just VF, right? There's no meaning V2F because both has the same velocity. Okay, so that actually the two momentum. Let's take a look the difference. Still in fourth decimal place level. If you see anything on the second decimal place level, you may need to take a look all the calculation again. Okay? Especially the table 1. I think something wrong there. That's why. Question. Okay, then rest is very simple. You just need to click and drag. Only 3 of them we can do together, okay? Because each case, earlier we had an issue with the table. Some columns are, some cells are merged. If you have a merged cell, I can't use the merged cell to do the calculation here. With the unmerged cell, that will be a problem for the Excel. Okay, these 3 we can do together. All right, you can see there's a changing momentum, but that's very close to the rounding error actually. If I rounded it, it may not be error at all for this kind of situation, but this case definitely not the rounding error. So which means they may be purposely putting some other little bit of error values to happen because we can then observe and then explain that. Okay, that's what my feeling is. So this may not be definitely rounding error. Okay, question. Okay, then let's continue. Let's do partially elastic. It's the same kind of calculation technically. Equal sign, parentheses, mass of the object number 1, 0.1937 multiplied by velocity of the object number 1 before collision, case partially elastic. So that should be G19, close bracket, plus parentheses, mass of the object 2.4811 multiply by velocity of the object 1 before collision, cell H19, close brackets, hit enter. And it's actually P final. Earlier I forgot to edit that. And then this is the initial. Also, I forgot to edit this too. This should be then I, and this should be I. Okay, these are just for the reference purposes. Make sure you understand all of those before you do any calculation. Okay, the functions. Copy paste this function also. Okay, that's total momentum before. Let's do total momentum after. Next cell. Equal sign parentheses mass of the object 1.1937 multiply by velocity of the object number 1 after collision cell I19 close bracket plus open brackets mass of the object 2.4811 multiply by velocity of the object 2 after collision cell value J19 close brackets hit enter. It's extremely similar. There's no difference at all. Difference is only on last decimal place. You can see it is 0.304. That's what the momentum conservation means. Doesn't matter what type of collision we study, you can see momentum is almost conserved. If I do rounding for the right significant figure, then I'm not going to see that number at all. I'm going to see zeros for all of them. So that's the idea, okay? Just copy paste this also. Question. It's going to be the final. Okay. Then the rest of the two you can just click and drag. You can see that case also the second one has a little bit of considerable error, but still if I rounded into second or even the third decimal place, second decimal place, still I will get definitely zeros for the changing momentum. Now those you have to explain, okay? Write it down 1 or 2 sentences for each case. Why the possible momentum change can be happen, even though it is not possible because we expecting friction to be 0 and then all of those, but you can consider the in-class real experiment setting and then you can write a couple of 1 or 2 sentences accordingly. Okay, question. All right, then let's take a look energy conservation. So energy is measured in joule, right? Newton meters. That I think everybody much familiar by now. And then we are interested here only kinetic energy, right? Because objects are moving only on horizontal plane. We actually interested only kinetic energy. So let's calculate again. Kinetic energy half mv squared equals sign parentheses half is 0.5 multiplied by mass of the object 1.1937 multiplied by velocity before collision object 1 cell value G13 power 2 plus open brackets half is 0.5 multiplied by mass of the object 2.4811 multiplied by velocity of the object 2 before collision h13 power 2 power is hat sign, okay, close brackets, hit enter. So this one also we should probably use 3 or 4 decimal places to see how we doing in terms of rounding, whether there's any rounding issues or not. Then we will see that. Now you can see that is affected, right? This number earlier 0.02, but that is not the case. It actually, in terms of it has a huge rounding error. Number is 0.0163. If I use only 2 decimal places, the error is so much. So we should actually use 3 or 4 decimal places. Okay. Right. So let's copy paste this one. This is the energy initial before collision equal half times mass m1 times v1I power 2 plus half times mass m2 times v2I power 2. Let us adjustment a little bit. This should be inside one parenthesis, and this should be inside another parenthesis altogether. And that's the command we use, right? Okay, question. All right, then let's do final energy. Equal sign parentheses, half is 0.5 plus mass of the object number 1, 0.1937 multiplied by velocity object number 1 after collision, cell value I13 power 2 close brackets plus open brackets half 0.5 multiplied by mass of the object number 2, 0.4811 multiplied by velocity of the object 2 after collision, cell value J13 power 2 close brackets. Hit enter. So that exactly same down to the 4th decimal place level. That's what exactly we expecting. So you can check maybe like 5th decimal place to see whether there's any possible changes are. Let's do that. These are calculated values. We are not interested sig figs at all here. What we interested is actually to investigate these conservation laws, right? Then you can see little bit of error. See that in 5th decimal place, which mean in terms of percent error or percent difference, almost gonna be like no meaning doing it. It's gonna be like 1% or even less than that, right? 0.001%. But it's still, if it shows like in the 5th decimal place, let's write it down what are the possibilities are, because you have a reason here, right, for the momentum change. So that reason is affected by here too. If you have a reason there, so the same reason, same kind of reason going to be affected to this observation too. But this is not huge energy loss at all, okay? Very, very small. So let's do the energy loss. ABS, we interested only the loss, okay? Now you can see this look like the final energy value is little bit larger than the initial. That almost impossible to happen in real life scenario. After collision, you will not get more energy of the whole system. You should get technically less energy on the whole system. Instead of, if I do without ABS, you can see the final is larger. It looks like energy is adding into the system. That impossible to happen during the collision. Okay. Let's do the change only ABS. So the final minus initial always difference. Very small, like the 5th decimal place. But if I consider into only 3rd decimal place, we will get perfect answer. But write it down like one sentence. You can mention that too. If I rounded into the right sig fig with the measured values, we observing the perfect conservation of energy. But if I don't round it, we see very, very slight difference. That difference may be result of the reason you had earlier in the case on table 2. Okay. Question. Okay, so these 3 cases I should get energy conserved. So we are good. It's still 4th decimal place level. You will see very slight difference next 2 cases, but it's still very small, extremely small value. Okay. However, now these next 6 cases, energy is not conserved. Okay, those are the information you have to really think about. These are very small numbers. Compared to that, next 6 cases, we should get fairly large values. Okay, that's the idea. If you're observing that, then we can separate out the collision type carefully. Inelastic means energy is not conserved. We should get larger values there. Next 3 definitely. But the last 3 may not be that large, but it still should be larger than the first 3. Okay, question. All right, let's do inelastic calculation then. Equal sign parentheses 0.5 multiplied by mass of the object 1.1937 multiplied by velocity for inelastic case 1 before collision power 2 close bracket plus open brackets 0.5 multiplied by mass of the object number 2.4811 multiplied by the velocity of the object number 2 before collision cell H16 power 2 close brackets. Okay, we have answered there. Let's do. Now this is same as the previous. Actually, you can even click and drag. I think it will do correctly that part. But only thing you can't click and drag is the final, because the next case final is different. Okay. So you remember final velocity is actually 1 for both objects. So I can't click and drag. I have to do that calculation. Okay. So let's do that here. Equal sign parentheses mass 1 plus mass 2 0.1937 plus 0.4811 close brackets multiplied by velocity is cell value I16 power 2 close. We don't need to close brackets there because masses are together, but the velocity is separated. We can leave it like that. Now you can see their energy loss is very large number. It's on the 2nd or 3rd decimal place level, but still it's very large compared to these 2 numbers. You can see easily, you can identify those 3. So only the first 3 you will get energy is conserved, okay? But none of the other cases energy, none of the other 6 energy conservation are not valid. Let me copy paste this function 2 to here. Only for final. Okay, and then we should go there. All right, question. Initially, same still, since the 2 velocities are separated, we can still click and drag. Initial case, it's going to be same this function, you don't need to retype, but the final you have to retype, okay? And the change should be very much larger. Now there you have to definitely explain why the change is really larger. It's not because of earlier reasons, okay? Not because of the reason you're trying to put it here. It because of it is inelastic. It is supposed to lose a lot of energy. So which means there may be sound, there may be heat energy, there may be other type of energy conversion from mechanical type, okay? So question? Okay, let's continue. Then this part I can click and drag. This one we can now click and drag all 3 actually. All right. So because it's the same case, now the cells are matched with the table number 1. When you do in one table to another, you have to make sure all the table that formatting is matching. Okay, if you have a different type of cells on 2 tables, you can't click and drag. Okay. All right, so you can see all of these numbers are very large, extremely large compared to previous values. See that? That's the idea of inelastic type collision. Energy must lost by large numbers. Okay. Question?
Professor.
Yeah.
For the inelastic cards moving on the same direction, what would you say is the explanation for energy final being higher?
Energy final actually, yeah, higher here, right? That's a good question actually. Energy increasing almost impossible really. Let us take a look at whether I did any mistake there. That possible 0.1937 plus 0.4811 I16 to the power 2. Let's see why is that really. Let me do that calculation again. That's a very good point. It's very unlikely. That's too big, right? This one, I16 to the power 2. Let's try with 0.183 power 2 to check whether we're getting the same answer. Yeah, I think nothing wrong with the calculation. So you have to think about what are the possibilities energy can increase. Can energy increase during the collision due to some reason? So energy increasing means some sort of external energy adding into this system. That's really very unlikely in like real life situation. I'm not really expecting energy to be increased at all. That's a very good point. So when you're explaining this particular part, this case only, okay, you not see other cases, right? In elastic card moving in the same direction, look like energy is adding together. So the one reason is that since the cards are moving in the same direction, when the cards are combined, then it's look like you actually putting the energy together. That's a possibility. But if the cards are in the opposite direction, the energy loss is going to be too high. So that's one possibility. Like the momentum is actually carry over from one card to another. But it's in real life scenario, any inelastic collision, energy adding into the system is very unlikely. That's a very good point. Just write up, think about it, and then come up with some ideas. Okay. Any other question? I highlight in different color because that actually something useful to take a look when we're doing the in-class work too. Okay, question. All right. So let's continue. Then next part, last calculation, equal sign. All the others, these two are fine. These two are general cases we generally observing. We can see energy lost by last numbers. Only this one we can let us keep that in mind. Maybe in class work actually we're going to do calculation in theory. Then we can take a look at any given point whether it's a possibility really. I would imagine definitely not. It almost impossible to happen. But there may be a physical situation it can happen because the energy is actually transferred from one object to another. Like the moment of transfer, it's not really losing the energy at all. So let us take a look at that little bit in detail later. Okay, let's continue. Equal sign, parentheses, partially elastic type collision. Still, I should get very large energy loss here too, right? So 0.5 multiplied by mass of the object number 1, 0.1937 multiplied by velocity of the object number 1 multiplied mass multiplied by 2 or the power 2 close brackets plus open brackets mass of the object number 1 times half 0.4811 multiplied by velocity of the object number 2 before the collision power 2. Okay, so let's check that with the final. Equal sign, you have to type the command always for the case number 1. Okay, case 0.5 mass of the object number 1 0.1937 times velocity of the object 1 after collision power 2 plus open brackets 0.5 times mass object 2.4811 multiplied by velocity of the object 2 final power 2 close brackets. Still very large difference. Okay, fairly considerable difference. Not extremely large, but it's still going to be considerable difference. 0.005. And the energies are on like second decimal place, lost is on third decimal place, so which means lost is more than 10%. So that definitely very large number, okay? Very large loss. Then rest you can just click and drag. So only different command happen only for this case. Every other case, the command is almost similar to this one, okay? So you can see all of these energy values are very much large lost. Only case we have to investigate little bit later at some point the case number one for the inelastic. That instead of energy loss, we actually observing energy adding up to the system. Okay, other than that, everything looks fine. So we expecting energy to be lost generally when the two objects collide, right? You hear sound, there may be heat energy, there may be part loss, for example, even that can happen. Object can be blow up into different pieces. So all of those actually result of energy loss, not really energy adding up. Okay, question.